The Earth is spinning about its axis. Here's the Earth viewed from the North Pole. As time passes, it rotates through a larger and larger angle. To describe how quickly this occurs, we use speed. The speed is just how much it rotates in radians divided by how long it took for that rotation to occur. Now, because we're talking about how many radians or degrees it rotates, we call that the angular displacement, theta. And because this is how quickly it rotates, we call that the angular speed, omega. In the case of the Earth, we know that the Earth makes one full rotation and it goes through 2 pi radians, or 360 degrees, in one day, which is 24 hours. Angular speed or angular velocity is very similar to ordinary linear velocity. The linear velocity is just the displacement divided by how long it took for that displacement to occur. And in this unit, we're going to see a lot of parallels between the linear quantities like linear velocity, linear displacement, and the angular quantities like angular velocity, angular displacement. As the Earth rotates, its rate of rotation, its angular velocity, stays the same. It's not rotating faster at 2 p.m. and then rotating slower at 4 p.m. But we can imagine scenarios where that's not the case. We're going to let these two balls roll down the ramps. Obviously, this one is going to speed up faster, and this one will speed up more slowly because the incline is steeper and shallower. Okay, let's watch them roll down. The arrow you see represents how fast they're going. Clearly, this one sped up quicker, and that one sped up more slowly. Now, let's look at their angular velocities. We're going to put a circle, and the circle will grow the faster they rotate. See, that angular velocity grows much quicker, and this angular velocity grows much slower. Remember that we use angular speed to talk about how fast it's rotating at any one moment. At the beginning, they weren't rotating at all, so the angular speed was 0. In the same way, they weren't moving at all, so their linear speed was also 0. But as time passed, the angular speed increased. So the same way we use acceleration to talk about how fast the velocity grows, we also use angular acceleration to talk about how quickly the angular speed grows. Now, I'm being a little careless right now when I talk about speed versus velocity. There is a distinction, and we're going to talk about the distinction with these angular quantities in more depth later. So, of the two balls as they rotated down, which one had a higher angular acceleration? Well, it's going to be this one over here, because its angular velocity, its rotation rate, grew very fast. And this one's angular velocity, its rotation rate, grew much slower. When we're talking about linear acceleration, we have equations that we can use to describe the motion of the object. S is the displacement, VI is the initial velocity, VF the final velocity, delta t is how much time has passed, and lastly, A is the acceleration. When we're talking about the angular quantities, we could easily talk about the final angular speed, the initial angular speed, the angular displacement, and the angular acceleration. And so the equations that we have on the left for linear motion are also true for angular motion and angular acceleration. So as the ball goes down, let's take 4 snapshots from here to here, right, from this moment at the top to this moment at halfway down. It has rotated exactly once, and you can see that because of where the slice is. The slice gets back to where it started. Okay, so what are the givens? What are the things that we know? It starts out with an angular velocity of 0, and I'm going to make up a value, and let's say this is given to us in the problem. At this moment right here, the angular speed or velocity is 0.5 radians per second. Because it starts and makes one revolution from here to here, how much angle has it rotated through? 2 pi radians. That's the angular displacement. Now let's say the problem asks us to find the angular acceleration. Which equation could we use? It would be this one, because we know this, it's 0.5, we know this, it's 0, and we know that, 2 pi. So we take the equation, and we're going to solve for the unknown. We plug in the value, 0.5, plug in the value of 0, and the value of theta, 2 pi, and with a little work we can solve to get 0.02 radians per second squared. Notice the unit is not meters per second squared because it's not regular linear acceleration. Rather, because we're dealing with angles, the unit is radians per second squared. Now, the same way that we can talk about angular speed and angular acceleration, there are angular forms of energy, and there's also rotational or angular mass. So let's investigate this using these spinning wheels. Well, they're not spinning yet, are they? To get them spinning, what do? I come over and I push on one, and it spins. Because it's spinning, you might think it has kinetic energy, but in fact what we say is it has rotational kinetic energy. And that's a different type from regular old kinetic energy where an object is actually moving left or right or up or down. If I come over to this one, I could give it some rotational kinetic energy. So I push on it. But wait, this one was a lot harder to spin. See how much slower it's going? I push the two equally hard. Now, this is not an unfamiliar idea. If you go out into an ice rink and you put your friend on your left and a little hockey puck on the right, if you push your friend with a force, the friend's not going to go very far. But if you push the hockey puck with the same force, its acceleration will be much greater. What's the difference between your friend and the puck? Well, the puck has a lot less mass, or inertia. Objects that rotate, they have inertia too, but it's slightly different. We call it rotational inertia or moment of inertia. And the greater the moment of inertia, the harder it is to get that thing accelerating or spinning. Good old-fashioned kinetic energy, which is called translational kinetic energy, is given by the formula 1/2 mass times speed squared. So what's the formula going to be for rotational kinetic energy? Well, instead of regular inertia, we need the rotational inertia, or the moment of inertia. We call that I, the moment of inertia. And instead of regular old linear speed, we use omega, which represents the angular speed.